The goal of this presentation is to tell you everything you need to know about linear algebra for solving systems of differential equations, or at least analyzing them, which aren't always the same thing. So, crash course in linear algebra. Before we begin, really, we need to establish some notation. First of all, I'm going to be referring to R, the bold-faced R, for the set of real numbers, and those will also be called scalars. And the real numbers can be visualized as a number line. And then R2, R squared, usually we call it R2. R2 is the Euclidean plane. The definition of R2 is it's the set of all ordered pairs of real numbers, and it's visualized with two axes, which gives you a plane, and we often call the first coordinate x, second coordinate y, and then each pair x comma y can be visualized as a point on this plane. And then R3 just means it have a third axis that comes out at you. We will often call it z. And just to be clear, usually this is not how we label the axes. Usually we have x coming out at you, y goes to the right, and z goes up. So this is not. But the point is, R3 is space. It consists of three axes, and so you can label any point in space using an x, y, and z coordinate. And while that is the limit of what our minds can visualize, there's nothing stopping us in mathematics from talking about n-dimensional space if we simply declare it to be the set of all ordered n tuples of numbers. So any list of n numbers can be thought of as a point in n-dimensional Euclidean space. And although you can't really draw a picture of it, it's nonetheless a thing. And then for notation, whenever we have a point in Euclidean n space, so this can be R2, R3, or Rn in general, the coordinates are numbers. And so those are italics for numbers, for scalars. Whereas the whole thing, the vector, is referred to with a bold letter, u, v, or x. You'll see lots of examples of this as we go forward, but I just want it to be clear that whenever I write a bold-faced letter, it's referring to a vector in a Euclidean space, whereas italics are referring to numbers. And the study of linear algebra boils down to the study of linear operators. These are functions from Euclidean space to Euclidean space with this property that if you apply the function to AU plus BV, where these are vectors scaled by the numbers a and b, then this is the same thing as adding the scalings of AU and AV separately. So it turns out that any linear operator can be represented by a matrix, a square, an n by n square of numbers, and so that when the matrix acts on a vector in Euclidean n space, it's given by this formula where you multiply the numbers in the nth row by the n coordinates to get the nth entry of the result. That's kind of hard to wrap your head around in general case, so it's best to look at an example in two-dimensional space to really understand what this is talking about. So here's an example. So a 45-degree counterclockwise rotation of the Euclidean plane is a function. It sends points in R2 to R2. And it turns out it's a linear operator, so it has that property from the previous slide with linear combinations. So the matrix, it turns out, is given by these numbers, and so if we take this matrix and multiply it by a vector, this is the result. So you take the numbers here, and they're multiplied by the components of your vector. And so the first component is root 2 over 2x minus root 2 over 2y, and the second component is root 2 over 2x plus root 2 over 2y. And it turns out this gives a rotation of the Euclidean plane. But if you don't believe me, let's look at the next slide. Imagine the Euclidean plane with a smiley face in it, and let's also label the two unit vectors 1, 0 and 0, 1, and they are blue and red respectively. And what happens when you multiply vectors and points by our matrix A is they map to a place on the Euclidean plane that's in a new location. And it turns out that A does this in just such a way that any image here is rotated counterclockwise by 45 degrees. So let's see how exactly that works. So let's look at the blue vector. The blue vector is 1, 0, and it goes to the blue vector over here, root 2 over 2, comma, root 2 over 2. Whereas the red vector, 0, 1, goes to the red vector, minus root 2 over 2, comma, root 2 over 2. Here's how that works as a matrix multiplication. If you take the matrix A and you multiply it by the blue vector 1, 0, that's this guy here, you to get the first component, you go across and down. Let me actually mark that for you. So you go across and down, and that gives you this number here, because it's root 2 over 2 times 1 plus negative root 2 over 2 times 0. So you're left with this. Whereas if we do the second row of the matrix, then you get the second component, which turns out is also root 2 over 2 plus 0 times root 2 over 2, so just root 2 over 2. So as you can see, doing this procedure shows that the blue vector, which was 1, 0, when you multiply it by the matrix, it ends up at the location root 2 over 2, root 2 over 2. And similarly, you can check that if you put a 0 here and a 1 here, 0, 1, you have the red vector, and you can check that that goes to negative root 2 over 2, comma, root 2 over 2, which is what I pictured over here. And then, moreover, you can check, you don't have to, you can take my word for it, but you can check that any point, say in the eyeball here or this mole over here, gets mapped to the corresponding point on the picture over here when you do this matrix multiplication. Right, so here's another example of a linear transformation that has a different matrix. And if you use this matrix, you get this picture. So this one's doing some pretty fancy stuff. First of all, it's doing some dilation, as you can see. So the blue vector goes here, and the red vector goes here. Actually, interestingly, this is an orientation reversing mapping, which is to say, in layman's terms, that the mole on the face goes from the right side of the face to the left side of the face. So now this person, well, all right, from the person's perspective, it was on the left side of his face, and now it's on the right side of his face. And that's called an orientation reversing linear transformation. Not that you need to know anything about that for this course. Just thought I'd throw that vocabulary at you for fun. The important thing to understand here is that all the same rules of matrix multiplication apply, and they do send the blue vector to this vector, the red vector to this red vector, and everything else is the same. The only thing that we changed is the numbers, and you get all sorts of different pictures. And here's another example of matrix multiplication. So you multiply the numbers in this row by the numbers in this column to get this number here, and you multiply the numbers in this row by the numbers in this column to get this number here. So this number here is 1 times 1 plus negative 1 times 0. So you end up with a 1 here. And as promised, this is the blue vector, and it maps to the blue vector on the right picture, 1/2, 1. So we have that. So in addition to distorting smiley faces and moving vectors to vectors, another important way to understand linear transformations is that it turns squares into parallelograms. This is a really important way of understanding linear transformations. Let me draw a picture. I believe this is the same transformation that we just had. It is. And now I've drawn a grid on the left-hand side, and I've shown what happens to the grid under the mapping by the linear transformation. And as you can see, each square in the grid has turned into a rectangle in the image grid. I should say, by the way, that this Euclidean space is called the domain, and this space is called the target, and whenever you have points here, the points over here are called the image. So points in the domain map to points in the image. And this whole space over here is called the target space. But anyway, so as I was saying, squares turn into parallelograms. Actually, by sheer coincidence, really, these happen to be rectangles. But in general, you get parallelograms, not necessarily rectangles. And then here's an interesting fact. If you take the determinant of this matrix, and the determinant just means you take these two numbers and multiply them together, and then you subtract these two numbers multiplied together, you get what's called the determinant, which for this matrix is negative 5/2. And this is a really important number. It's called the stretch. You could think of it as the stretch factor. It says how much the area of the squares gets stretched when you apply the linear transformation. So this linear transformation stretches the squares by a factor of 5/2, meaning that the rectangles over here have area 2.5 times the area of these squares, who have area 1. The negative sign, if you're curious, indicates that this is an orientation reversing linear transformation. So if you have an orientation preserving linear transformation, such as the 45-degree rotation that we considered in the previous example, that would always have a positive determinant. And if it's orientation reversing, it so happens that it will have a negative determinant. And we're not going to prove any of those facts in this course, but we will take for granted that the determinant of a matrix tells us how much it stretches squares to produce the parallelograms in the image. So every single linear transformation that we've considered so far has been a bijection, meaning it gives a one-to-one correspondence between the domain and the target space over here. What do I mean by one-to-one correspondence, you might ask? Well, take any point here, such as this one. This is the point 2, 3, and it maps over. Actually, you can't even really see it, I don't think. It would map over here. But that's not really my point. The point is that For each point here maps to a specific point over here, but more can be said. If you take any point on the right-hand side, like this point here, there's always going to be exactly one point from the domain that maps to it. Because that's really important, I'll say it again. For each point on the right-hand side, there's exactly one point on the left-hand side that maps to it, and that's called. We say that this mapping is a bijection, if that's true. Not all mappings are bijections. In fact, not even all linear transformations are bijections. But if you do have a bijection, then you can also define what's called an inverse map, which is the mapping that takes points over here and maps them back to the points that they came from. That's called the inverse map. So by definition, the inverse map has the property that A inverse of A of x equals x. So that's the defining property of the inverse map, and also similarly A of A inverse of x is x. So if you have a bijection, you can always find an inverse function. But and this is the definition of a bijection from an abstract standpoint, in case you're curious. And if the columns are close to parallel, then a pretty bizarre thing happens to the image. It gets very distorted, as you can see. So that's because this first column says where the blue vector goes. The second column says where the red vector goes, and since they're almost parallel, the image gets very squeezed along this direction. You can barely even tell that it was a smiley face to start with. So the more parallel these columns in the matrix, the smaller the determinant, it turns out. So because recall the determinant says the stretch factor of the matrix, but as you can see, if these vectors get very close together, these parallelograms will be so thin that their area will be very small, and therefore they will have a tiny determinant. The matrix will have a tiny determinant. So a small determinant says the image is getting compressed. On the other hand, if you have perfectly parallel columns, then it turns out the image is completely squished to a line, because this blue vector and this red vector, they're both mapped to they're parallel. One's mapped to 1, 2, the other's mapped to 2, 4. They're parallel, so the entire image is actually squeezed onto this line. So it's no longer a bijection. I mean, take any point. Say, take this point right here where my laser pointer is, and there's literally no point in all of space that maps to that point. It is no longer in the image or the range of our function. So our range or our image has been compressed to a single line through the origin. And when a transformation is not a bijection, when it fails to have that property that each point here has exactly one point here that maps to it, when a transformation fails to have that property, we call it singular. So this is your first example of a singular transformation. And singular transformations have an interesting property. If you have a singular transformation, then we can find vectors, which are called null vectors of A, such that the transformation A maps x to 0, to the 0 vector, that is, to the origin. There are vectors here that map to the origin. Let's find them. Turns out this vector, which for cosmetic purposes, I put it on so that it points to the edge of the face. But you could say that this vector is -2, 1. And you can check that A times this vector, -2, 1, equals 0, 0. So this vector is mapped to the origin by this transformation. In fact, all vectors on this line will map to the origin. And this line, by the way, this black line of the set, is the set of all vectors in Euclidean 2 space, such that the transformation maps them to 0, is called the null space of the transformation. So we have visualized the null space of this transformation. The vectors on this line are mapped to the origin. All other vectors are mapped somewhere else along this line. And all these vectors can be represented with by the formula -2k, k. So I just kind of gave that to you, but let's do an example of calculating a null space. I have two transformations here, A and B. Let's visualize them, and can you tell me which one is singular? Well, and then in the second part, we're going to find the null space of the singular matrix. Beginning with the first part of visualizing them. Actually, I haven't written this lab yet, but anyway, we will visualize these two transformations. Here's our smiley face, and here's what it looks like in the image when we use the matrix A. As you can see, it looks, it is definitely not a singular matrix. It is a bijection. So that's what it looks like. That's all I have to say about it. Non-singular. On the other hand, if we look at B, B does compress the image onto a line. And there's a couple ways you could have seen that. One is that the determinant of B is 0. The determinant of B is 1 times 2 minus -1 times -2, which is 0. So, if the determinant is 0, that means that B is compressing squares onto parallelograms of area 0. The only explanation for which is that it's compressing them onto a line. The other way of understanding this is just to say, well, this is the blue vector, this is the red vector, they're parallel, and therefore the transformation maps the entire plane onto the line containing those two vectors. However you choose to think about it is fine, but there are different ways of understanding the fact that a transformation is singular. Right, so now we're going to find the null space. So recall what that means. If a matrix is singular, it'll have null vectors, vectors that map to the origin, that map to 0. And we want to find them. So let's go ahead and take a vector x, let's call its coordinates, its components x and y, and we're trying to find vectors that map to the origin. So here's what that looks like. We're looking for a vector x, y, such that when you multiply it by this matrix, you get 0 and 0. So here's what that is. When you write out the definition of matrix multiplication, you get this system of equations. The first component is 0, second component is 0. Now usually, the only solution you could possibly have to a system like this is 0 and 0. But it turns out these equations are redundant. See, the second equation is just -1 times the first equation, which means that, so we see by inspection then, that if you just solve the first equation, then the second equation is automatically also satisfied. So you can just plug in any number you want. I plugged in 1 for y, and then I automatically got 2 for x, so that 2 minus 2 is 0, and then the second equation is automatically satisfied. So 2, 1 is a solution for x and y. So I went ahead and plotted that vector here, 2, 1, and then the null space is the entire line 2k, k, which I've also plotted here. And so all vectors on this black line will actually map to the origin when multiplied by the matrix B. So we just calculated our first null space. So here's an important problem. It's the Eigen problem. If you have a matrix A, try to find all vectors x with the property that AX is parallel to x. Meaning that if you take your vector on the left-hand side in the image, you take the corresponding vector on the right-hand side, I'm interested in finding a vector that's parallel to its image, which might actually sound impossible for some transformations, but remarkably, it always is possible. So let's take a look at this problem visually first. Here's what our transformation looks like, and we're looking for vectors that are parallel to their image. Well, I found 2 of them for you. This purple guy maps, if you look at the corresponding purple vector in the image, it's parallel, so that is one solution to this problem. And then also this green vector is parallel, happens to be pointing in the opposite direction, but parallel nonetheless, is parallel to its image. So purple and green are the 2 solutions to this problem. And it turns out there aren't any others. So you can check algebraically that A times 1, 0 is 3, 0. So that's saying that the blue vector maps to 3 times the blue vector. And you can also check that the green vector, 1, 2, maps to -2, -4. So it maps to a vector that's twice as long but pointing in the opposite direction. But the point is, they're parallel to their image. So I've gone ahead and I want you to also note that the green vector and the purple vector, technically they're not the only solutions to this problem. Technically any vector on the purple line is a solution to this problem, and any vector along the green line is also a solution to this problem. Any vector on the green line would map to a vector along a line here, and any vector on the purple line would map to a vector on a purple line here, if we were to draw them. But I went ahead and I erased the grid, as you can see. I did that kind of sneakily, because I'm going to draw a new grid parallel to the purple and green vectors. And if you erase the grid over here and draw the image of this grid has a remarkable property that the grid in the domain is parallel everywhere to the grid in the image. So by finding these special vectors, you are also finding these directions along which the transformation does not rotate or shear space. So the transformation does just pure dilation along these directions. So now I want to show you how I found those green and purple vectors. Those, by the way, are called Eigen Vectors. Solutions to the Eigen Problem are called Eigen Vectors. Suppose x is such a vector. If you're trying to find an eigenvector, here's how you do it. You're trying to find a vector who's parallel to his image. So you want it to be that a times x is a scalar multiple of x. That's what it means for two vectors to be parallel. Now, if you let the coordinates of this vector be x and y, then the equation ax equals lambda x becomes this system of equations if you look at the components. Now, if you subtract over all this stuff on the right-hand side to the left-hand side, and you combine like terms, you end up with this, with the 3 minus lambda times x minus 5 halves y equals 0. And over here we have 0x plus negative 2 minus lambda y equals 0. So I've just written this as a system of equations in x and y. And if you can then write it in matrix form, like so. So we're trying to find a solution to this system of equations. But this matrix here can be written as the original matrix, 3, negative 5 halves, 0, negative 2, minus lambdas along the diagonal. So if you subtract lambda times this matrix from this matrix, you get this matrix. So this matrix is just A minus lambdas along the diagonal, which you can cleverly rewrite as A minus lambda I, where I is the identity matrix. So A minus lambda I x equals 0. So we conclude that in order to solve the Eigen problem, you need to solve this problem. But how do you solve this problem? Well, recall that if you have a matrix times a vector equals 0, that's saying that this vector is in the null space of this matrix. If you call this matrix B, B only has null vectors if its determinant is 0. So what this fact is saying is that this problem is only possible if we choose lambda such that the determinant of this matrix is 0. So if we want determinant of A minus lambda I to be 0, you can expand out the definition of the determinant, and you end up with this quadratic in lambda, which boils down to telling us that lambda is 3 or negative 2. So again, the Eigen problem only has solutions if we pick lambda here to be 3 or negative 2, otherwise it simply won't be possible. If lambda is 3, so we subtract 3 along the diagonal of A, and you end up with this system of equations, which is really easy to solve. You just get 1, 0. I'll leave that as an exercise for the student. And similarly, if you subtract negative 2i from A, then this system becomes this, which also has a pretty simple solution, 1, 2. And you'll recall those are the purple and green vectors that we found on the previous slide.